Good morning, everybody. Today we'll be discussing the chapter thermodynamics. Then we just having a chapter at a glance, so that this will help us to solve the case set and neat questions in a proper way. So without wasting our time, let us just start with the chapter thermodynamics. So the terms utilized in thermodynamics first is system, surrounding, and boundary. System, the quantity of matter or region in space chosen for study is a system. Surrounding, the mass of the region outside the system is a surrounding. Boundary is a real or imaginary surface that separates the system from the surrounding. So boundaries can be fixed or movable, shared by both system and the surrounding. No thickness, no mass, or volume. Okay, so this is just a way in which a system surrounding and boundary can be visualized. Then we can talk about the types of the systems. There are three types of the systems: open system, closed system, and isolated system. Open system is a system that can exchange matter as well as energy with the surroundings. Closed system is a system which cannot exchange matter but can exchange energy with the surroundings. Isolated system is a system which cannot exchange matter as well as energy is called an isolated system. So just I tried to show here an open system and closed system and an isolated system. So this way in which we can talk about the systems here. Now the state function, when we talk, it is defined as a property whose value depends upon the state of the system and is independent of the path by which the state has been reached. For example, a person is standing on the roof of a building, has a fixed value of potential energy, and the potential energy of the person does not depend on how he reached it, either by stairs or by lift or anyhow. So that is what is said to be a state function, which depends only on the initial and the final state, but does not depend on the path which he has taken to reach that. So thermodynamic properties, when we talk about property, what is actually a property? It is any measurable or observable characteristics of the substance when the system remains in equilibrium state: pressure, temperature, density, volume, energy, specific volume. There are two properties which are related to a system, that is intensive property and extensive property. Intensive properties are those properties which does not depend on the mass of the system. Extensive properties are those which depend on the mass of the system. So intensive property which does not depend on the mass of the system: temperature, pressure, density, specific volume, etc. These properties are independent on the mass of the system. These properties remain same. Extensive properties are those like total energy, volume, etc. So we can talk about state, path, and process. Condition of a system as defined by properties of a system is known as a state of a system. Series of state of a system through which a process occurs is known as path of a system. Any change of state of a system is known as a process. So we know that isobaric process, pressure remains constant; isothermal, temperature remains constant; isobaric, volume remains constant; isotropic, isoentropic means entropy remains constant. So that is how we talk about the that is state function and path function. Point function is nothing but state function or path function. And any quantity whose change is independent of the path is known as the path function. That is a state function. Any quantity, the value which depends on the path, is known as path function. The magnitude of such quantity, that is state quantities, depends on the state. The magnitude of such quantity is equal to the area under the curve on the property diagram. They are exact differential, they are inexact differential. Inexact differential is denoted by delta. Properties are the examples of state functions. Here are pressure, volume, temperature, energy. Heat and work are path functions. So thermodynamic processes can be reversible process, irreversible process, cyclic process. Reversible process, change must occur in successive stages of infinitesimal quantities, infinite duration. Virtual thermodynamic equilibrium at each of the small stages. Changes of thermodynamic quantities in the different stages will be the same as in the forward direction but opposite in sign with respect to forward direction. System and the surrounding can be put back in their original states by exactly reversing the process. Irreversible process, real or spontaneous, occur suddenly or spontaneously without restriction of occurring in successive stages of infinitesimal quantities. Irreversible processes cannot be undone by exactly reversing the change to the system. Do not remain in the virtual equilibrium due to the transition. The work in the forward and the backward processes would be unequal. Cyclic process is one in which the initial and the final states are the same. In such processes, there is no change in the state variables. In contrast, path functions generally have non-zero values for cyclic processes depending on the path. So isobaric, isovolumetric is nothing but isochoric, isothermic, and adiabatic. Isobaric is nothing but the pressure remains constant. Isocoric is nothing but volume remains constant. Isothermic is nothing but temperature remains constant. Adiabatic means not, that is heat content of the system remains constant. So that is the different types of processes. The first law of thermodynamics states that the change in internal energy delta U of a system is equal to the heat Q put into the system minus the work W done by the system. So here delta U is equal to Q plus W. See here the rotations used for Q and W depends on whether heat is lost or heat is gained by the system, or work is done or work is done on the system or work is done by the system. Depending on that, the sign conventions changes. Here, isothermal process. So the work done in an isothermal process can be easily calculated by using the equation here. Isothermal, we know that temperature of the system remains constant. Therefore, we say delta U is equal to zero, and delta U is equal to Q minus work done by the system, or delta U is equal to Q minus done by the system, or Q is equal to W work done by the system, or Q is equal to W. Here we can say the work done from state 1 is equal to P dV, or we can even write the formula as P is equal to nRT ln V2 minus V2 by V1, or W is equal to nRT ln P1 by V2. Instead of using ln, you can even use the equation as W is equal to 2.303 nRT log V2 by V1, or 2.303 nRT log P1 by V2. So the graph easily tells you about the change here. Then the adiabatic process, for an adiabatic process, PV raised to gamma is equal to a constant. With the help of PV is equal to nRT, this can be expressed as T B gamma raised to gamma minus 1 is constant. T gamma by P raised to gamma minus 1 is constant. Adiabatic process, when we talk about, it is PdV NR plus CV by CV plus VdP. We can say NR plus CV is equal to CP. Gamma here we can calculate easily as CP by CV. So adiabatic process, the internal energy can be calculated. Change in internal energy is equal to NCV delta T, or work done will be equal to minus CV by R. P final, V final minus P original, V original. So isobaric process, we can say W is equal to minus P delta V, or is equal to minus P V final minus V initial. Work by the system in is the area under a PV graph. Work is a path dependent, which I have already discussed. Whenever it is a path dependent, it will be the area covered under the things there. Isochoric or isometric processes, here we can see here for an isochoric process, W is equal to 0, no work is done. And since delta V is equal to 0, delta U is equal to Q minus W, and delta V is equal to, so delta U is equal to Q. So work is not done in an isochoric process. Then we talk about the exothermic and endothermic reactions. Exothermic reactions which release energy to the surroundings. Endothermic reactions are which absorb energy from the surroundings. Temperature of the surrounding increases in exothermic, and in endothermic, the temperature of the surroundings decreases. So yes, where you can show the two different exo and endothermic reactions. Relationship of delta H and delta E. There is a relationship between delta H and delta E, that is the internal energy and enthalpy of a system. So the delta H is equal to delta E plus P delta V. So instead of P delta V, we can even write it as RT delta N. Delta H is equal to delta E plus RT delta N, where delta N gives us a clear relationship between delta H and delta V. Measurement of enthalpy change. It is quite impossible to calculate the absolute enthalpy of a system directly. Hence, we can calculate the enthalpy about a reference point. Therefore, we generally measure the change in enthalpy change. Delta H is positive for endothermic reactions, while it is negative for exothermic reactions. Measurement of enthalpy change in laboratory is done through calorimetry techniques. We know that enthalpy change is a heat change at constant pressure, that is delta H is equal to QP. Coefficient uh, coffee cup calorimeter is often used to calculate the enthalpy change. In this technique, the cup is partially filled with a known volume of water, and a thermometer is inserted through the lid of the cup and such that its bulb is below the water surface. When a chemical reaction occurs, the heat of the reaction is observed by the water. The change in the water temperature is used to calculate the amount of heat that has been absorbed or evolved, since the cup is made up of polystyrene foam, a very good insulator. Very little heat energy escapes. Energy change or enthalpy change in this process is calculated as delta H is equal to QP is equal to mCp delta T. Here you can even write N. mCp delta T is equal M, where is mass of water, Cp specific heat capacity of water at constant pressure, delta T is temperature difference. So the calculation is done in this way using the cup what is being told, and it is made up of a polystyrene material which is a very good insulator. So measurement of change in internal energy. Internal energy change is the energy change at constant volume. Bob calorimeter is generally used for the measurement of internal energy change. In this technique, a steel vessel, commonly called bob, is immersed in a water bath in order to ensure that no heat is lost to the surrounding. A combustible substance is burned in oxygen gas supplied in the bob. Heat is absorbed by the water around the bob, and the change in the temperature is measured. Energy changes associated with the reaction are measured at constant volume. As volume doesn't change in is the completely sealed bob calorimeter. As the volume remains constant, work done is zero for the system. Energy change or internal energy in the process is calculated as delta U is equal to QV is equal to mCV delta T. So, in general, enthalpy is called as heat content of a system at constant pressure, and internal energy is called as heat content of a system at constant volume. So, keep that in mind whenever we are referring delta H and delta U. Delta H is nothing but heat content of the system at constant pressure, and internal energy is nothing but heat content of a system at constant volume. So the Bob calorimeter is referred in this way, and accordingly the calculations are made. And now let us talk about the enthalpies of reactions. There are various enthalpies of reaction: enthalpy of formation, enthalpy of combustion, enthalpy of neutralization, enthalpy of hydration, enthalpy of transition, enthalpy of sublimation, enthalpy of fusion. Enthalpy of formation. Enthalpy of formation, when we talk about enthalpy of formation, is that when one mole of a given compound is formed from its elements. Combustion is when 1 mole of a substance is burnt in excess of air or oxygen. Enthalpy of neutralization is 1 gram equivalent of an acid is neutralized by 1 gram equivalent of a base in a dilute solution. Enthalpy of hydration, when a salt combines with a required number of moles of water to form specific hydrate. Enthalpy of transition, when 1 mole of a substance is transformed from one electropic form to another electropic form. Sublimation, when 1 mole of a solid substance sublimes at a constant temperature and 1 bar pressure. Fusion, enthalpy change when 1 mole of solid melts. So these are the examples for each category of enthalpies. So let us talk about the lattice energy. Lattice energy is nothing but a change in energy that takes place when separated gaseous ions are packed together to form an ionic solid. This can be in a vice versa also. A solid salt getting ionized to give the respective gaseous ions. The energy change or the enthalpy change that occurs. To calculate lattice energy, a beautiful example is given of NaCl, that is in the form of Born-Haber cycle, in which you can just look at here. You can have a thing here. When we are having NaCl, Na solid and half. So Na solid and half Cl2 gas. First, this solid is getting converted to gas. That is, sodium is getting converted to gas. And after it is getting converted to gas, that is called as solid. When it is converted to gas, it is called as sublimation. And when gas is getting converted to an ion, it is atomization. And then chlorine is getting, here again chlorine is getting atomized, that is again atomization. And then chlorine is um, yeah, both the ions are combining to form NaCl. So that is how you are calculating the lattice energy by summing up all the enthalpies of this together. We get the that is the lattice enthalpy of sodium chloride, which is calculated as minus 80 minus 787 kilojoules per mole. Now, Hess law. Hess law is stated as if a chemical change can be made to take place in two or more different ways, whether in one step or two steps or more steps, the amount of total heat change is same no matter by which method that change is brought. When a reaction is taking place in one single step or in multiple steps, the change in enthalpy that occurs is same. So you can see that in the first way, carbon is getting converted to carbon dioxide in a single step. In the second case, you can see that first it is getting converted to carbon monoxide and then this is converted to carbon dioxide. So this whether it is in a single step or in a multiple step, the change in enthalpy remains the same. Bond energy. So the bond energy is defined as the average amount of energy required to break all bonds of a particular type in 1 mole of a substance. That is breaking up of the bonds. The bond energy depends on size of the atom, electronegativity, and bond length. We can just calculate the bond energy as delta H is equal to summation of H bonds broken minus summation of H bonds formed. That is reactants minus products. That is how we can say that. Entropy. Entropy is a measure of molecular disorder or molecular randomness. As a system becomes more disordered, the positions of the molecules become less predictable and the entropy increases. Entropy is defined as ds is equal to dq by t, kilojoules per Kelvin. The entropy change can be obtained by integration. So entropy change is equal to delta S q by T naught. Here, entropy is related to enthalpy. And you can see here, when we talk about three states of matter, solids, liquids, and gaseous, randomness starts increasing from solids to gaseous. The randomness is more in gas, lesser in liquids, and comparatively lesser in solids. So entropy is maximum in gas and minimum in solids. Gibbs free energy, which we have given delta G is equal to delta H minus T delta S. Gibbs equation helps us in knowing the spontaneity of a reaction. So to know the spontaneity of a reaction depending on the values of delta H and delta S, we can predict the value of delta G and predict whether the reaction is spontaneous or not. So you can look at here, when delta H is negative and delta S is positive, delta G is all the time negative. That means reaction is spontaneous at all the temperatures. So reaction is spontaneous at all the temperatures. If delta H is positive, delta H is negative and delta H is also negative, yani delta H and delta S both are negative, delta G may be positive or negative. That means when is the reaction spontaneous and when is the reaction non-spontaneous? The reaction is spontaneous at low temperatures, whereas non-spontaneous at high temperatures. When both are negative, when delta H and delta S both are negative, the reaction is spontaneous at low temperature, whereas non-spontaneous at high temperature. Next, when delta H is positive and delta S is negative, the delta G is positive always. That means the reaction is non-spontaneous at all the temperatures. That is, it is a non-spontaneous reaction. When both are positive, when delta H and delta S both are positive, delta G may be negative or positive. That means the reaction when it is spontaneous and when it is non-spontaneous. It is spontaneous at high temperature and it is non-spontaneous at low temperature. So that is how we have to remember. If delta H is negative and delta S is positive, spontaneous at all the temperatures. If delta H is positive and delta S is negative, non-spontaneous at all. If delta H and delta S both are negative, it may be spontaneous or non-spontaneous. If delta S and delta S both are positive, again it is spontaneous and non-spontaneous depending on that. What condition? Temperature. If both are negative, spontaneous at low temperature. If both are positive, spontaneous at high temperature. So that point you have to be remembering. Now let us talk about free energy and the equilibrium constant. We know that equilibrium constant delta G naught is equal to minus RT ln K equilibrium. Instead of writing ln, we can even write it as minus 2.303 RT log K. So predict the things here, but depending on the equilibrium constant, delta G's values can be predicted. If delta G naught is less than 0, that means it is negative. K value is greater than 1. That is product are favored. Any forward direction reaction takes place. If delta G naught is equal to 0, then K will be equal to 1 at equilibrium. If delta G naught is greater than 0, then K is less than 1 and the backward reaction is taking place. So free energy and equilibrium constants help us to calculate equilibrium constant also and to predict the uh, product formation also. So that is all about this.